All right, in this video, I'm going to show you how to implement logistic regression in Python. And the example that I'm going to use for this application is the same example that I used for the OLS regression. So I am going to use the California housing dataset and continue off of the code that we were building in the previous video. I will put the link to the previous video that we discussed how to implement OLS regression to predict housing prices in California so that you can watch it. And this is going to be a continuation of that. Now, the big difference between the OLS regression that we did and the logistic regression that we are going to do is the fact that we are going to have a different target variable. The target variable for the OLS regression was the median housing value for the districts in California. In other words, there we were working with a continuous variable, which was basically the median value of houses within a district. Here, in order to demonstrate how logistic regression works, I am going to create a new variable, which is going to determine whether the house is expensive or not. And it's a very subjective term, so I'm just going to say if a house is worth more than $250,000, I'm going to label it expensive. Otherwise, I'm going to label it not expensive, right? So basically, I'm going to create a new binary variable that determines whether a house is expensive or not. In other words, determines whether the house is more expensive than $250,000 or not. And then would run logistic regression to basically predict that likelihood and also determine the factors that affect the likelihood of the house being an expensive house. And then we are going to compare the predictions and the estimates from the logistic regression with the OLS regression that we did in the previous video. All right, so let me start by creating the features and label data set. So I just comment here, create the features and labels data sets. And what I am going to do is to use the cleaned data set. And if you remember, the cleaned data set was the housing underscore clean. So I'm going to use the same data set and create a new variable. I'm going to call it expensive with a question mark in front of it. And I'm then going to call numpy or np here and create a new column that is going to be based on the values of the median house value column. So I say np where in the housing clean data set, and we're working with the variable median house prices. So I'm going to just copy and paste it from up here. Median house value. I just say where it's larger than 250,000, equal it 1, otherwise 0. All right, so what I'm doing here is that I'm creating a new column called expensive question mark that is going to be added to this housing clean data set. And that column is based on a logical argument. If the median housing value is larger than $250,000, the value of that column variable is going to be 1. Otherwise, in that column, the observations value is going to be 0. Okay? So let me run this and then show you how the data looks like. So you see that we have added a new column called expensive. And you see that in all of the first 5 observations, because the median housing value is over $250,000, the value of the expensive is equal to 1. In cases where it is not the case and the value of the house is less than $250,000, then this expensive variable is going to be 0. All right, to create the features data set, which we used to call it the capital X data set, now I have to drop two things. The very first one is that I have to drop the median house value, because this is something that we are not going to predict. We are not going to use in our predictions. The median house value was actually the target, so this has to be dropped. And also the expensive, this is the one that is going to be dropped. So the features data set, I am going to call it X2 so that I'm not confusing it with the original X data set that only included the features for the OLS regression. So I'm going to call it X2, and X2 is basically going to be this data set that we have, except the fact that there are two columns that I am dropping. So I said drops, open the parentheses, and I identify the columns inside brackets, and the columns that I'm going to drop are the median house value. Make sure that you put them in quotes. So median house value and expensive. And remember, this X2 is basically identical to the X data set that we had created previously. So you can even skip this part as long as you remember to update your code accordingly in the next step. Now, what is more important is your Y2, which is the features data set, and the label data set. And the label data set is going to be the housing clean that only includes the expensive column, okay? And this is what we are going to have here. So the main difference between OLS and logistic regression that we're doing here is in the label data set, in basically the Y data set. We used to call it Y, but here I'm going to call it Y2 for consistency in the next step. You will realize in a second. And the difference is that Y2, the values are either 0 or 1, indicating whether the house is expensive or not. And then here I'm going to basically calling the train test split function again. I'm going to call my training and testing data sets X2 and Y2 test and train respectively. So X2 train, X2 test, Y2 train, and Y2 test is going to be equal to train test split, and then the data sets are X2 and Y2. I'm going to use the same ratio as the previous, the 20% for splitting the data set, and I'm going to use the random state of 1984 as always, right? So this would create the training and testing data sets for me. Now, in order to use the logistic regression, you have to import it from linear models library in sklearn. So go ahead and type in from sklearn dot linear underscore model import logistic regression. Again, pay attention to capital L and capital R. And then, just like before, I'm going to just call it a name so that it's going to be easier for me to call it down in my code. So I just create a function called logistic, which is basically going to be whatever this logistic regression is for me. And again, following the same structure as previous code, we just say logistic.fit and then give it the set of features and the label for train data sets. Make sure that you're correctly identifying X2 train and Y2 train in your data set. Okay. And then the warning that you get here is that the maximum number of iterations has reached. You can increase the number of iterations, but don't worry about this. The regression model is running for you despite this warning that you get. So also let me score this data set. So I'm going to say logistic.score based on X2 test and Y2 test to see how well I'm doing here. You see that the score is 83%. Now, if you want this to be in a nicer format rather than being this long number to have it in like a percentage format, you can actually do this. So let me put it in an object. So I call it logistic underscore accuracy is equal to this. And then I can actually give it a format and just type in logistic accuracy is equal to make sure that this is inside the quotation marks. So basically what I am doing here is giving a particular format to this logistic accuracy. And what I'm doing here is that I'm saying that I want to have 2 decimal points and in terms of percentages. The way that I got this is basically just Google searching to see what are the potential formats that I can use here. And you see that this is the format that I am using here because it is going to create the output that I intend. So the accuracy that I have is currently as a number in this format, and I want it to be like a percentage. So I look at the Python documentation, and this is what I have to use based on what Python recommends to me. That is why I did that. And the rest of this code is that once you've typed in that, you have to type in format and use the name of the variable again within parentheses. And what you do, it basically goes and changes the format of that variable for you. So you can go to just to see how it looks, print accuracy of the logistic regression is, and then add the logistic accuracy as a string variable here to see how it works. And you see that it types in the accuracy of the logistic regression is 84%. It is a much nicer format to look at the accuracy in this context. Now, this is how the logistic regression is done in Python. However, the problem that we have here is that, again, just like OLS, it is not very easy to look at the coefficients of these variables when it comes to the logistic regression. We know that some variables, some observations are labeled expensive, some are labeled inexpensive, and the inexpensive and the accuracy of our logistic regression is 84%, which is not really superb. However, just like OLS, the advantage of logistic regression is in its capability to explain. So it is going to show us how each of these variables are affecting the outcome, and that is what we really want to look at. We want to look at the table of the results that shows the estimated coefficients for all of the variables in our model. So just like the OLS regression, which we had to import other libraries for a better representation of the results, we're going to do the same. For the OLS regression, we relied on the statmodels.api, and that is the same library that we are going to do here. So again, to refresh your mind, note that previously in this code, I have already imported statmodels.api and called it SM, and I am going to use that library here and basically use the logit function. So sm.logit is the name of the logit function within the stats model library. And again, remember that in the stats model, the order in which you identify the features and training data sets are in reverse. So while in linear models of sklearn, you had to identify the features first and then the training data set. What we are doing here is that and then the labels data set. What we are doing here is that we first identify the labels data set and then the training data set. And then there's a bit of a difference in the syntax as well, and that is that you have to type in .fit. So I'm going to call this function nicer logistic and once it's run, I can actually go ahead and type in print nicer logistic dot summary. Don't forget the parenthesis. And once I do that, I get the summary table for the logistic regression, something that is very similar to the summary table that we got for the nicer OLS function that we ran before. And actually, if you just type in nicer logistic.summary without including the print, then you get a format that is exactly like the format of the OLS regression. All right, and the way to interpret these coefficients is basically the unit is basically to say how much one unit of increase in each of these variables affect the log odds of the dependent variable, which in this case is the house being expensive, okay? The interesting thing to note here is that although the coefficients are obviously not the same as the coefficients that we estimated for the OLS regression, they are similar in their signs. So previously, when we looked at the OLS regressions, for example, we saw that latitude has a negative coefficient, indicating that as we go north, the price decreases, right? That is the negative coefficient implies here. And we have the same thing for the estimate of latitude in the logistic regression, indicating that as we go north, the log odds of the house being an expensive one decreases. The last thing that I want to mention when it comes to interpreting the results is when we have transformed our categorical variable to binary ones. You remember that we did this with the location variable that was indicating whether the house is in is an island or not. And what we did was that we dropped one of these binary variables. We had a variable that was indicating whether the house is in an island, and I said that you have to drop it. Now, once you drop that variable, that becomes your baseline. So you're going to compare and interpret the results of the estimates of the remaining binary variables in comparison to that. So when you look at the results from the OLS complex regression, you're going to say that the coefficient of inland is, say, negative 1.8 multiplied by 10 to the power of 5, which is basically equal to roughly $187,000, right? And the coefficient is negative. So the way that you interpret it is that the median housing value of the houses that are in districts that are located inland is $187,000 less than those that are located in islands. And the same goes for the others. So when you look at these four variables, you would see that the houses inland are the least expensive ones compared to the ones that are on an island. And then the next one is going to be the ones that are, say, near ocean, right? So the houses that are near ocean are roughly $145,000 cheaper than the ones that are in an island. If they are within an hour of the ocean, then they are only $149,000 less expensive than the ones on islands, and so forth. Now, when you go and look at the results from the logistic regressions, again, you would interpret them accordingly. So when you're looking at, say, the coefficient of inland, you would say that the houses that are located in the districts that are inland, their log odds of being expensive is 147 units less than the ones that are in island.